Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. Today we will start with angular momentum and we'll continue with it in the next two videos of this series. First, we will state the definition of angular momentum. After that, we will work the angular momentum of a circular motion and then of a symmetric object. So let's start. Great, let's start by finding the angular momentum of a point particle. Angular momentum is going to be measured with respect to an axis. So once we have our particle here with mass m and velocity v, we need to establish an axis with respect to which we're going to measure its angular momentum. We can choose any axis, and for instance, we're going to choose the axis pointing perpendicular to the board that crosses it at this point, and we'll call it the s-axis. Now we're going to establish a vector pointing from this point to this mass, and note that this vector is going to be perpendicular to the axis. We'll call it rs. Now, in analogy to how we define torque, for example, that if you remember, it's T equals R cross F, we're going to define angular momentum through this axis to be L through S equals RS cross P, which in this case is equal to MRS cross B. Note that doing the right hand rule, we find that the cross product is going to point towards the inside. As we go over there, then we curl and it points towards the inside. So we determine that the angular momentum in this situation is going to be pointing to the inside with a magnitude of mRV. However, we observe that angular momentum really depends on our choice of axis, of reference axis, as if we choose our reference axis to be over here, for example, we're going to find, and we'll call this S prime, we're going to have this vector rs prime, and in this case, doing the right hand rule, we observe that L prime over here, it's going to be pointing outside of the board. This one towards the inside and this one towards the outside. So just by choosing different reference points, we find that the angular momentum can even change directions. However, something that we'll prove in one of the following videos is that if the total momentum of our system is equal to 0, which we can easily observe in here, we give 0 to this quantity, the angular momentum is the same independently of the reference point that we choose. This assumption, this statement is trivial for one particle, but for multi-particle systems that we'll explore in following videos, it's really useful. Let us make some other remarks. Note that independently of the reference point, the angular momentum is always going to be perpendicular to the vector rs, and it's also going to be perpendicular to the momentum vector. Moreover, if we examine the units of this quantity, angular momentum, we're going to find that is equal to kilograms meters per second times meter, which equals kilograms meters squared. And those are some of the most important things you need to know about angular momentum. Great. Now let's calculate the angular momentum of a particle doing a circular motion. Let's imagine we have this axis, and then we have a particle over here that is going around executing this circular motion along a circle of radius r. We're going to call this axis S. This will be the k hat direction. And then we'll have the r hat direction and the theta hat direction. In this setup, we're going to measure the angular momentum along this axis S. So, by definition, from the previous section, we know that the angular momentum L is equal to Rs cross P. Moreover, in this case, Rs is just R in the, Rs equals R in the R hat direction. And our velocity in this direction, let me draw it, P, it's equal, so momentum equals mb, which equals mb in the theta hat, the direction that we have, in the theta hat direction. Moreover, we know that this velocity is related to the angular velocity by b equals rw. So we have that this is equal to m, the radius r, w in the z direction, as this is going like this. It's going around, and it's going to the k hat direction in the z direction, and this is in the theta hat. Because in here we're only changing magnitudes. The total vectorial expression would be b equals w cross r, which could give us the velocity, like this, the velocity in the right direction. Now that we've established these two expressions, we can substitute them in the expression for our angular momentum, and we get that L in the s-axis equals, thus we get this expression, and with the right hand rule we can calculate this cross product from r to theta that goes k hat. So we have that this is equal to m r squared wc in the k hat direction. And in here we recognize two things. First of all, this is identically equal to the moment of inertia of this particle around that axis. So we have I in this axis. Moreover, this is the angular velocity of this object, W. So we observe that the angular momentum, and this is a very important expression, of a particle is equal to its moment of inertia times its angular velocity. And we know that this expression is remarkably similar to its linear analogous, P equals mb, where m is substituted by the moment of inertia and v by the angular velocity. Great, now let us consider the angular momentum of a symmetric object. We found on the previous section that for a single mass, the angular momentum around the axis around which it goes around was equal to mr squared, the moment of inertia, times its angular velocity. In this case, for this symmetric object, we're going to take two masses that are going to be at opposite sides of the axis. So we'll take, here's more delta m, and over here at the opposite point, at the diametrically opposite point, another delta m, which are going to be of the same size. Then, taking advantage of what we said in the first section and we will prove on the next sections, we observe that the total momentum of this system of two particles that we're considering is at every point in time 0. Therefore, our angular momentum is going to be independent of the axis of reference to which we measure it. The angular momentum is going to be the same at every point with respect to every point of reference in space. knowing this, we can use still this formula, as angular momentum can be superposed. If we have two particles with a set of angular momentum each, we can just add those two angular momentums. In this case, both of them point towards the same direction, so they add to each other, and we find that in this system, through this axis, per equals 2 delta m r squared w. But we can denote this L per, and this can be independent of the axis of reference that we took, because we will prove that as the total momentum is 0, this is the case. Then we just need to sum over every pair, or better yet, do an integral. So we would integrate over the mass and of 2dm. So we're really integrating over like the pairs, mass of pairs, because we don't want to integrate twice everything, such that this is dm pair. And then we also have r squared w that are outside of the integral. Therefore, this is going to give us m r squared w. And this again is the moment of inertia of this ring that we have. So we conclude that the total angular momentum, is going to be equal to the moment of inertia around this axis, and this is important because this part is indeed with respect to the axis of rotation, and then W is also with respect to the axis of rotation, specifically the axis of symmetry of this object. Because if this axis is not the axis of symmetry, then the angular momentum is going to be dependent on our choice of reference axis for the angular momentum. But if we choose it as the axis of symmetry of our object, then it's going to be independent. Moreover, using differential analysis, we can see that we can easily extend this to a disk, as this is the angular momentum for the ring, but when we add this expression, W is the same for all different rings of different sizes, so we can integrate over them, and we're just going to have a different moment of inertia. And then we can also integrate in 3D to create some nice shapes. So we could find, for instance, a shape. Imagine it's symmetrical. It doesn't look quite symmetrical on the board, but if this shape was symmetrical, its angular momentum, and if it's obviously rotating at the same angular speed as the others, its angular momentum would be the exact same as for the ring, just with a different moment of inertia. Great, that's all for today. I hope that you understood everything and you got a sense of angular momentum, some pretty simple applications of its principles, and how you can calculate it in general for symmetrical objects. In the following videos, we'll explore more deeply this quantity that is really useful in circular motion problems. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, subscribe to the channel and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!